Hello everybody and welcome to another video. Today I'd like to talk about solving the two-dimensional wave equation. If you remember, in our last video we talked about how to derive the 2D wave equation, and furthermore, if you've been following along with our video series on partial differential equations, you know that we've already discussed how to solve the 1D wave equation and several forms of the heat equation using the separation of variables technique. To solve the 2D wave equation, we'll employ a similar technique with a few small twists. So in order to avoid duplicating discussion that we've already covered in previous videos, I'm going to go fairly quickly through the process here and only discuss nuances that are new and we haven't seen before. Therefore, I would recommend going back and watching both of these videos on the screen before continuing with the lesson today. So I'll leave a link to both those videos in the description below. So if all of this sounds good, why don't we jump on over to the whiteboard and get started. Alright, so why don't we go ahead and start by just stating here the 2D wave equation problem. We'd like to pose this nicely before we get started. So if you remember, we said our two-dimensional wave equation was d squared u dt squared is equal to c squared plus the Laplacian of u. So something that like this, right? Partial u with respect to y squared. Right? Okay, so this was our PDE that we're interested in solving. We also had some boundary conditions for the problem. So the boundary conditions that we would like to consider here are that u of x, y, and t, right? This is the function that we're looking to solve for here. This is going to be equal to 0 for all x, y on boundary. Right? So here is our boundary condition. Right? So this corresponds to everywhere along basically the edge of this membrane is fixed and does not deflect, right? Okay. In addition to the boundary condition, we have some initial conditions. Namely, we'd like to say that the initial displacement is equal to some two-dimensional function f of x, y. Something like this here, right? So here's our initial condition for displacement. And we'd also like to say that maybe the membrane has some initial velocity here, right? So the derivative of displacement with respect to time is obviously the velocity of the displacement, or the velocity of the membrane here. So this at time 0 has got to equal some other function. Let's call this thing, how about g of xy? So here's our initial condition for velocity, right? So with all of that stated here, here's what we're looking for here, right? Here's our PDE, here's our boundary condition, here's our initial condition here, and now the goal here is basically just find ourselves some function of x, y, and t here, right, that satisfies the PDE, the boundary conditions, and the initial conditions, right? That's the goal. So the way we're going to do this here is let's consider here an example. I always like to work with concrete examples here. So let's look at, how about a rectangular membrane? So in other words, let's just sketch this thing out in maybe the x, y plane here. We would like to look at some membrane that looks like this here, right? It has a width of a height of b, something like this. Let's call this thing region R, and the region R is where this thing is going to be vibrating in and out of the plane here. So I guess if you want to, we could draw this here as the deflection is coming in and out of the plane here, right? So here's the problem here. We're going to solve this in, again, 3 steps here. So step 1 here is, again, we're going to do our separation of variables. However, we're going to have to do this twice. So what we're first going to do is we're going to first say that, okay, u of x, y, and t here, we are going to try to break this thing up into a spatial function. Let's call it big F of x, y, right, times a temporal function, g of t here, okay? So this first separation of variables didn't quite get us all the way because we see that this is still sort of a PDE effectively here, and an ODE is what we're going to end up with. So we're going to have to perform another separation of variables and set f of x, y, right? We're going to try to separate that again into a function which is only a function of x, let's call that h, times a function which is only a function of y. Let's call that thing q here, right? So this is actually 2 separations of variables here. Okay? And then once we have that, step 2 is going to be very similar to what we saw earlier. Well, once we have those two, we're going to go ahead and try to find eigenfunctions. Basically, we're going to find our u, and we're going to see that u is going to be a function of m and n, two integers, similar to what we saw in the steady state heat equation solutions here. Once we have these eigenfunctions which satisfy, right, our boundary conditions, right? That's what those eigenfunctions did. We can move on to step 3 here, which was our total solution, right? Via Fourier, right? And the idea is this total solution will then satisfy our initial conditions as well, okay? So that's our game plan, 3-step process here. Like I said, we're going to go a little bit quickly through each one of these 3 because by now you've already seen this with our 1D wave equation, our heat equation, our steady state heat equation, Laplace's equation. So we've done this before, so let's zip through this now. All right, so why don't we go ahead and get started? So like we said here, step 1 here is we're actually going to do 2 successive separation of variables. Okay, so what we're going to do here is, again, we said our function u is a function of independence variable x, y, and t here. Let's first do a single separation of variables by splitting this into a function which is only dependent on the spatial variables multiplied by a product which is dependent on the temporal variables. Okay, so now let's go ahead and sub this into the 2D wave equation. And again, since we've seen this many, many times, I'm going to skip a couple of steps here, but we'll basically go ahead and substitute this in, take appropriate partials, divide things through, do a little bit of manipulation here. And at the end of the day, what you could do here is you can manipulate this thing to look like, so I'll just use this dot, dot, dot to represent various manipulations. Again, they're just simple algebraic manipulations, but in the interest of time, let's just say that you can basically get this thing to look like a g double dot over c squared g is equal to 1 over f times fxx plus fyy. Again, noting here that we're using the double dots here to denote derivatives with respect to time here, and the xx or the yy subscripts are derivatives, in fact, 2 derivatives with respect to x, 2 derivatives with respect to y here. So again, this is what the 2D wave equation looks like if you assume this solution type here. So what we notice here is, again, we see that the left-hand side is just temporal variables. The right-hand side is just spatial variables. So we're going to make the exact same argument we did earlier and say that, you know what? These two things have to equal some separation constant here, right? And you can make that exact same argument that we did in previous videos showing that this has to be a negative value. So let's go ahead and denote this thing as, how about negative nu squared? Okay, so what we end up out of this is basically 2 differential equations. So basically this side, right, we can say here's g dot dot over c squared g has better equal negative nu squared. And then similarly 1 over f times fxx plus fyy has got to also equal negative nu squared here, right? So why don't we rewrite these here? So this first ODE here, we can actually rewrite that to look a little bit like g double dot plus a lambda squared g has got to equal 0 here. And in this case, lambda here, you can kind of see it's just basically some combination of c and nu. In fact, it's just c times nu. And then this one down here, we can rewrite this sucker to look a little bit like fxx plus fyy plus nu squared f is equal to 0 here, right? So let's look at these two. So this first one up here, this is just a normal linear second order ODE, right? And in fact, since we can see here that since c and nu, well, tell you what, we'll get to this later here, but again, this is something we've seen a million times before, right? This is just a undamped oscillator, right? Now this second one right down here, this is actually, we don't get an ODE, we get a PDE, right? Because f is a function of x and y, and there are derivatives with respect to both x and y in here, right? So we actually end up with another PDE. And actually, this is another very famous partial differential equation. This is sometimes, well, actually, this is called the two-dimensional Helmholtz equation. Okay, so that's going to be kind of interesting here. So what we need to do here is we still have a PDE in the form of the Helmholtz equation. Let's do another separation of variables here. So let's do this. We'll write down sep of variables number 2 on the Helmholtz equation. Okay, so here we're going to say, all right, I've got this function f of x, y here. Let's assume that the solution to the Helmholtz equation can be written as the product of a function which is just a function of x times a function which is just a function of y here, right? So we do the exact same thing we did earlier, right? Sub this into the Helmholtz equation, right? Do a couple of various manipulations here, and basically what you can get this thing to look like is just like we did earlier. This is boring manipulation, so I'll just write this as various manipulations. Right, this second separation of variables, you're going to get this thing to look like 1 over h times dh squared dx squared is equal to 1 over q, and actually that's a negative here, times dq dy squared plus nu squared q here. So again, notice here we dropped the partial notation because, right, h and q are only a function of one variable, so there's no real need to talk about partials versus total substantive derivatives, so it's the same thing. But anyway, here we go. Same thing here. Let's go ahead and make the exact same logic here, that the left-hand side is only a function of x, the right-hand side is only a function of y here. So again, this has to equal a separation constant. Same thing, we need to have this thing be negative to avoid a trivial solution. So let's call this separation constant, how about minus k squared here? Okay. So here we go. We end up now with, we set the left side equal to minus k squared. So we have 1 over h times d squared h dx squared is equal to minus k squared. And then we set the right-hand side, right, of negative 1 over q times dq dy squared plus nu squared q has got to equal negative k squared, right? Okay, and then again, we can basically, sorry, I'm pointing at the wrong thing. This thing, we could rewrite this in a slightly nicer fashion here, that it might look like a more reasonable ODE that we've seen before here. So this thing could be rewritten as dh dx squared plus k squared h is equal to 0. Okay, and then this second ODE down here, we could rewrite this whole thing to look like dq squared dy squared plus, let's call it a p times q is equal to 0 here. And in this case, p, you can kind of see right here, p is just a mixture of this, the nu and the k here, right? I'm just going to rewrite it as a different variable. So p squared is going to be nu squared minus k squared. Okay, and again, this might be worth noting here that we're going to use this notation to show that this p squared thing is supposed to be positive here. We're going to see we need that in order to avoid a non-trivial solution later on down the road. So here we go. We have it. Here's an ODE. Here's an ODE, and then back here was a third ODE. So great. By basically applying separation of variables 2 successive times here, we're able to take our one PDE, which was our 2D wave equation, right, and break it up now into 3 separate ODEs, right? Okay, so now I think that's the end of step 1. Let's go to step 2, where we go ahead and try to satisfy the boundary conditions by solving these ODEs. Actually, sorry, I'm back. Before we do step 2, I made a small typo over here that I want to correct. Over here, this should be a p squared, right? So just maybe just correct your notes here that in this third ODE for q, that should be a p squared there. Okay, all right, now that I fixed that typo, now let's go do step 2 and satisfy the boundary conditions. All right, so I've erased the board here, so let's go ahead and move on to step 2, which is trying to satisfy the boundary conditions, right? Okay, so tell you what, let's go ahead and start with our ODE for h, right? So we said the ODE governing h was this thing, right? Plus k squared h is equal to 0 here, right? Just looking at this, again, we notice linear second order undamped oscillator, ODE here, right? So pretty much I can pull the solution of this directly from our discussion of ordinary differential equations, and we see that, okay, the function that's going to solve this thing, it's something like a cosine kx plus b sine kx. All right? Similarly, let's look here at the ODE for q here, right? So that is dq squared dy squared plus p squared, right? Remember, I made that little typo with p versus p squared. It should be a p squared here, right? Q is equal to 0. Again, you'll look at this thing exactly the same thing, right? Linear second order, homogeneous, ordinary differential equation. So the solution to this guy is really similar here, right? It's, whoops, sorry, this should be a q. The solution for this guy is q of y should be c cosine of py plus d sine of py. Great. Okay, so here's our two candidate solutions. Let's talk about now the boundary condition here. So if you remember here, our boundary condition is we stated here that we want the deflection of this system to be equal to 0 for all t on the boundary. Right? So since we said u here, this thing was given as, we said, two successive separation of variables, right? So the first one here was f of xy times g of t is equal, we need to see equal to 0, again, on the boundary, right? For that same condition. So again, since t is independent of the spatial derivatives, we see that this basically puts a restriction here on what f can look like. So we basically can say that, all right, f of xy has got to equal 0 on the boundary here. Right? Okay, so let's take a look here at our diagram here. I think earlier we said we were investigating this scenario of the rectangular membrane here. So let's take a look at how does this boundary condition translate for all of those conditions here, right? So let's go ahead and look at here, how about the left side? Right, so on the left side of that boundary, we're basically saying that, all right, the function f at x equals 0 and at any given location y here, this has to equal 0, right? Okay, so then where was our, oh, sorry, we should have probably mentioned, right, f here, maybe we should have written it down here, maybe, because if you remember here, our f function, we did another separation of variables here, right? And we said f here was actually going to be the product here of, I just want to make sure I keep the notation similar, right? H of x and then q of y, right? Okay, so f at x equals 0 basically means h at x equals 0 times qy has to equal 0, right? So this is the same thing as basically saying h at 0 times q of y has got to equal 0, right? And again, we can make the same argument that since q of y is kind of arbitrary here, right, this basically means that h has to be 0. So finally, the long logic of this here is what we end up with here, right? So the left side being fixed basically trickles down and all the way basically says that, all right, your function h at times 0 had better equal 0. How about the right side? Okay, so same thing. We said, all right, right side being fixed basically states that f when x is equal to a, here, lower a, this, and at any given y has got to equal 0, right? So we saw that that translates into h of a times q of y had better equal 0, which again translates into h of a is equal to 0, right? Okay, how about the bottom? We can make very similar arguments, right? So the bottom, we said that, all right, now, at any given location x, but at y equals 0, that better have 0 deflection, right? That's at the bottom of this rectangular membrane here. Okay, so then that basically states that, all right, your function h of x times q when y equals 0 has to equal 0, and now it's h of x that can be arbitrary, so this is really a restriction on q. And particularly, q at times 0 had better equal, or at y equals 0 had better equal 0. And lastly here, the top side, we're saying that at any given x location, but at y is equal to b, has to be undeflected, which relates to a restriction on Q at y equals b equals 0, right? So great. So all of this discussion on the boundary condition basically gave us this column here, which are 4 boundary conditions to these 2 solutions here that we saw earlier. So let's just apply these conditions to these 2 to see what are the restrictions now on A, B, C, D, or potentially K and P here, right, of these parameters. What do those have to be in order to satisfy these 4 boundary conditions here, right? Okay, so let's go ahead and do that right now. Maybe a good spot to do that here is, tell you what, let's erase this. We don't need any of this anymore. Okay, so let's go ahead and apply the h of 0 is equal to 0 condition. Right, so that's basically the left side here. So h of 0 is equal to 0, so I just plug in 0 here, and we end up with, well, a has got to equal 0. Great, that's one solution. How about now let's apply the h at x equals a has got to equal 0 condition. Okay, so again, take this expression here, plug in when x is equal to a, and combine this with the fact that we know a is 0. And we end up with here that b sine of ak had better equal 0. So to avoid a trivial solution, we don't want b to be 0, we want this term to be 0. So we see that that places a restriction on k here, right? K, the product ak has to be some multiple of pi. Or the other way to say that here is k has got to equal some m pi over a here for m in the integers, right? That's one of our restrictions, okay? You do the exact same analysis here for the other side, for the top and bottom. So let's apply the q of 0 is equal to 0 condition, right? So just plug in y is equal to 0 here. We end up with c is equal to 0. Perfect. Now you go ahead and apply the q at y equals b is equal to the 0 condition, right? And we get the exact same discussion here. That, long story short, at the end of the day, well, I'll tell you what, maybe we should, let's not skip it. Let's make everything similar here. So we saw c, this is 0 here. So we end up with d sine of pb has got to equal 0 here. So therefore pb has got to equal some multiple of pi, or we see p then has to take on values. Where did I put that here? Oh yeah, of some, you know, n pi over b for n in the integers, right? So again, they're very, very similar, but we see now that k and p are not free, just like we saw earlier, except now we've got 2 of these to deal with, not just 1. Okay, great. All right, trucking right along here. So with that in mind here, we see that the general solutions for h and q, maybe we can call them h of x here, right? This is going to be something like a b sine of m pi over ax with m some integer value here. And again, since we see that this has a different family of solutions for m equals 1, 2, 3, 4, etc., let's maybe put a subscript m down here, right? Similarly for q, right, we see here that this is going to basically be like a d sine n pi over by for n in the integers. Again, let's maybe adopt a subscript sub n, right? So finally what we have here is our solution to the Helmholtz equation, right? We said that was f of xy, and we said that it's the product of these two, right? It's hm of x times qn of y, right? And again, we see since these have indices of m and n here, maybe we should call this thing like an fmn here. Right? Okay, so let's just plug these in and see what this looks like here. So h of m, that's this guy up here, right? It's a b sine of m pi over ax. Q here is this guy, so this is a d sine of n pi over by. Right? You see this b and d, they're arbitrary constants, and they're a product of 2 arbitrary constants, so they maybe make another arbitrary constant. Why don't we call this thing gamma here? So let's just say let gamma, capital gamma, equal b times d here, right? So if so, what we can do is we end up with, here's our solution to the Helmholtz equation. It's some arbitrary constant gamma times sine of m pi over ax times sine of n pi over by, with m and n forced to be integer values. So great, here we go. We've gone ahead and solved our Helmholtz equation, right? The last thing I maybe want to do here is let's revisit the Helmholtz equation before we declare complete victory, because there's one other interesting nuance that maybe we haven't seen before. Is if you recall our Helmholtz equation, we've said that this whole thing is supposed to solve the second order differential equation, right? The Helmholtz equation, right? This thing was something like fxx plus fyy plus nu squared f is equal to 0. Right? Okay, so what we better do now is stick this expression into our PDE here. So in other words, right, we need to take the second, well actually, now I better use partials, right, because this is now talking partials, yeah. So this is partial with respect to x squared of that whole thing, right, of gamma sine of m pi over ax times sine of n pi over by, right? This thing plus basically, whoops, this should be dy now, right? Because I'm doing this term here, right? Of the same thing here, right? So maybe I'll just say same here, right? Jamming that equation here, plus nu squared times the solution here. So again, same, right? So if you do, and this better equals 0, okay? If you do this here, so actually this is at this point you can see it's boring algebra manipulations here, right? You just need to take the second partial of this thing with respect to x. It's actually not that bad. You see that this is basically just going to pop out what, like a m pi over a squared and like a negative sign when you take the derivative of this twice here. Tell you what, let me spare you the details here, or tell you what, we'll go over in Mathematica in a second. I don't want to break our pace here, but we'll go to Mathematica and do this just to show that I'm not doing crazy mumbo jumbo, but I am just lazy and don't want to do all these algebraic manipulations by hand on the board. What you'll end up with here is, at the end of the day here, you end up with something that looks like this. You end up with nu squared has got to equal m pi over a squared plus n pi over b squared, okay? So what this basically states here is that, yes, this is a solution to the Helmholtz equation, but only if nu square has this very specific value here, right? Then this will all equal 0, right? And you know what? Maybe we should take a break and go to Mathematica just so we can verify two things. Let's verify that A, this thing satisfies the Helmholtz equation, and furthermore, it only satisfies the Helmholtz equation if this is the actual value of nu here, right? So again, let's just go to Mathematica and plug this in and see what we get. All right, so let's go ahead and first define the function f of mn, right? No, sorry, that should be capital F of mn of x and y, right? We said this was our solution, and we said that this guy was a function of x and y, and it was given by, I believe, gamma sine of m pi all over a x times sine of n pi over b y, right? So here was our solution. And now what we probably want to do here is show that this satisfies the BCs, right? All of the boundary conditions here. So we can go ahead and check here that this thing, let's do the left side here, right? So this should equal 0, right? That's our left condition, and yeah, that's true. Let's check how about the right condition, right? The right side is when x is equal to a, I believe, that should equal 0. And as we saw, in general, that's not true unless we go ahead and simplify this and basically say that, you know what, m is in the integers, right? Oh, come on. Oh, sorry. I'm having a real hard time with my cap locks here. Okay, is in the integers, right? As well as n is also an integer value only, right? All right, let's try this now. This simplification with both those, and we see, yep, now it's true here. So, okay, we got the left and the right side work. Let's go ahead and check the top and the bottom here. So, the bottom here was for any x and for y equals 0, this better equals 0, and the top condition was for any x and for a y is equal to b, that should equal 0. And yay, here we are. So everything worked out in this case. We see that this solution does satisfy the boundary conditions. Now, let's go ahead and verify that this solves the Helmholtz equation, that PDE, right? So, in order to do that, we basically need to go ahead and we need to take its second derivative a bunch of times, right? So we have the derivative of x and y here, right, with respect to x twice. So here is fxx, right? fxx plus fyy, like this, all right? So there we go. We got fxx plus fyy plus, what do we have, nu squared or something like that? Let me just write this as, how about a v squared or something like that? Actually, you know what? Let's call it a single variable. V. Yeah, well, I guess we could do that, right? Let's see. See, v squared here is equal to fmn, x and y. Right? This had better equal 0 was our game plan here, right? And as you can see here, no, in general, that's not true. Let's try to go ahead and make our little simplification and say that, you know what? M and n also need to be integers. So let's go and say simplify this thing with the idea that m and n are integer values. And we see that, whoops, what did I end up doing? Oh, I got too many brackets. We see it's still not true here, right? The reason why is, again, we said earlier, gamma can't be absolutely anything you want, right? Gamma has to be a very specific value. So you know what we might want to do here is, let's go ahead and solve this thing. Let me erase this here. Solve this for nu here. Sorry, I might have misspoke earlier. I said nu is the thing that has to be specific. Gamma is an arbitrary constant here. So let's do this. So we see here's our solution here for nu. And actually, I kind of want to get rid of this plus or minus. Tell you what, let's write this as a single variable. How about nu squared? I just want to make this like nu squared. There we go. Okay. So it needs to look like this. This is the specific value of nu squared that is going to make our solution f solve the Helmholtz equation here. And I think you might have noticed that this is not exactly the same thing that we had on the board here, but it is, in fact. So I think on the board we had, we claimed here that the value of nu had to be something like m pi over a squared plus n pi over b squared, something like this. Let's just double check that this is actually the same thing as this expression up here. Right, and maybe let's go ahead and simplify this. And it is. So we see that this is the very specific value of nu that has to happen here in order for our candidate solution to satisfy the Helmholtz equation. So let's go back to the whiteboard and continue working on building up our eigenfunction, but now we understand that nu actually has to take a very specific value here. M and n have to be integers, but nu also has to have this very specific format here in order for everything to work out. All right, so now we show that, all right, this is the very specific value of nu that we need to solve the Helmholtz equation. Let's turn our attention to the temporal ODE. So to refresh your memory, that was just g double dot, effectively, of t, right, plus lambda squared g of t is equal to 0 here. So in this case here, lambda we said was c times nu here, right? And when we actually derived this earlier, we said that one of the separation constants, if you remember, we had this second separation constant we said was p squared, which was actually nu squared minus k squared here. Or in other words, nu was equal to p squared plus k squared to the 1/2. right? Let's substitute this into our expression for lambda here, right? So we could basically write this thing as lambda over c is equal to p squared plus k squared to the 1/2, right? Or lambda equals just c times this thing, right? Times p squared plus k squared to the 1/2, right? And now, if you remember earlier, we showed that k and p, these things were constrained to be specific values here. So if you recall, right, we said that k has got to equal some m pi over a here, and we said that p had to be n pi over b, right? Okay, so substituting that into here, we see that our final expression for lambda here, lambda is something like a, you could write that like this, right? C pi times the quantity n over b squared plus m over a squared to the 1/2, right? So we see here that, again, C, this was something like tension over density or something like that. This was all physical parameters of the problem here, but n and m were integer values, right? So again, maybe we should adopt the notation here that this lambda value here has an m and an n subscript here, right? So there's a different lambda for each m and a different lambda for each n here, right? So these are effectively your eigenvalues of the system here, right? Because you can see that they're basically telling you, this is basically lambda mn here, right? It's telling you how fast this system oscillates here. So here are the eigenvalues, right? Because what we can do here now is basically directly solve this second order ODE now, right? So if we do that here, we can basically directly write the solution to the temporal ODE, right? It's, you see, it's a second order undamped linear oscillator here. So we end up here with G, whoops, sorry. The solution of this thing, G of t, right, is going to be something like a, let's make it some arbitrary constant. It's called BMN. Cosine of lambda mnt, well, excuse me, plus another arbitrary constant. How about a bmn star times sine of lambda mnt, right? And again, let's maybe adopt the notation here, since all of these frequencies change here. Maybe each one of these we should say is a different solution, like an mn here. Great. Okay, so here's the solution to our temporal ODE. We already had the solution to the Helmholtz spatial PDE effectively here, which was right here. So the total solution for the entire original PDE is the product of this times this here, right? Because if you remember, well, we ended up with how we started this whole double separation of variables principle, right, was we said that the total function u of x, y, and t, right, this is going to be the spatial one times the temporal solution here. So f, we saw this was mn. This was our solution to the Helmholtz. G of mn was what we just got here by solving the temporal ODE. So really we see that we have, this is like an mn here again as well, right? So for each different m and for each different n, we get a different solution here. So great, let's just plug these in. So this guy for the Helmholtz, this was our, what the heck was this thing? Why did I write it like this? I should have had it backwards. Okay, well anyway, this is fine. So this was our gamma sine of m pi over ax times sine of n pi over by, right? Times our temporal guy here, which maybe I'll start a different line here because it was this kind of longer expression here. So this is a bmn cosine lambda mnt plus a bmn star sine of lambda mnt. Great, something like that. And now I think you can see here that we could distribute these gamma through to each one of these terms. So I could move this gamma in here and put a gamma here and a gosh, I'm running out of room. This a gamma, whoops, not an f, a gamma here. But again, this is now arbitrary constant times an arbitrary constant. That's just another arbitrary constant. Same thing right here. So maybe the easier thing to do is without a loss of generality, we can just go ahead and let gamma equal 1, right? So I don't have to keep carrying this extra arbitrary parameter around, since it could be consumed by these two arbitrary parameters if you'd like here. So, all right, maybe let's rearrange this here. Maybe I'll write this first here. Let's write the total solution. So we end up with UMN as a function of x, y, and t here. It's here it is. It's this guy right here. It's I guess really, like I said, it doesn't matter what order. Maybe let's just write this one first for giggles, for something different. So it's BMN cosine of lambda MNT plus BMN star sine of lambda MNT, right? Times sine of m pi over ax times sine of n pi over by. There we go. And actually, let me erase some of this so we don't... And I'll keep our expression for the eigenvalues here, because this is what we're looking at here, right? This is what we were trying to get. So here is our eigenfunction here, right? So here's the eigenfunction, right? We claim that this is going to satisfy the original complete PDE that we started with, namely the 2D wave equation. And here are the associated eigenvalues, or you can kind of see it's the frequency of oscillation if you want to think about it that way. So I think we're pretty much, that defines everything. The only other parameter maybe that might be helpful to rewrite here is this C parameter here, right? If we said earlier C here, I think this was just square root of the tension divided by the density here, right? So great. I think we've basically got it right here, right? Here's the eigenfunction, here's the eigenvalue here. What we should maybe do is let's jump over to Mathematica here and verify that this thing solves the boundary conditions and solves the initial PDE that we're interested in. And then what might be interesting too is maybe let's go ahead and plot a couple of these guys here. So before we jump over to Mathematica, maybe let's set the stage here for this. Let's look at an example here of a square membrane, where this is like A is equal to B is equal to something similar. So instead of a rectangular membrane, you have a square membrane. What makes that kind of interesting here is we're going to see that then there are actually different solutions here which yield the exact same eigenvalue. You can see if A and B are the same, you could have like n is equal to 2 and m is equal to 1. That is going to give you the exact same value as if you had n equal to 1 and m equal to 2 here, right? So what we're going to see here is there are multiple combos of m and n which yield the same lambda mn. But what's interesting is we should look here and see what are the corresponding eigenfunctions for each one of these eigenvalues. We're going to actually see that even though you could have the same frequency of oscillation, you could have completely different shapes, right? We said these could be interpreted as mode shapes of your vibrating membrane here. So let's go over here to Mathematica and take a look at this. Let's plot these up. Well, first, let's go ahead and define this, check that it satisfies the boundary conditions, check that it satisfies the partial differential equation, and then plot a couple of examples for this square rectangular membrane here. Or sorry, for the square membrane. All right, so let's go ahead and define our function g mn of t, right? This was our solution to the temporal equation, and I believe first maybe what we should do is define the eigenvalues, because we saw that the solution gmn is a function of those eigenvalues. So I think we said this was c pi times the quantity n over b. I think this thing was squared, right? Plus the ratio of m over a squared, and this whole thing was square rooted, right? Okay, and now with that in mind, we can say that, all right, gmn, I think we said this was bmn times cosine of lambda mnt plus bmn star times sine of lambda mnt. Great. Okay, so There we go. We've got our GMN. So let's go ahead and define the eigenfunction, right? Right, this is what we're looking for, and I think the easy way to do that is, since we already have most of these functions defined in our notebook here, we said that this was just fmn of xy times gmn of t, and I think we made one other simplification, namely we said that without a loss of generality, there's no need to be carrying this gamma around, so let's go and replace that right here. So let's say gamma of just 1 to start with. Okay, so here we are. Here is our eigenfunction. So now what we should do here is let's go ahead and verify that this satisfies, maybe instead of using pronouns like this, let's actually be very specific. Let's just say that our eigenfunction satisfies, satisfies the boundary conditions here, okay? So, again, on the left side, that was at x equals 0, any y, and at any given time, this better equals 0. Yay, that worked out. We also now need, on the right side, that at, at x equals, let me see, what was it? X equals a, I think, right? This has got to equal 0, and again, we run into this issue here, so we probably better make sure that we simplify and say that, you know what, this is only valid if m is in the integers. I always have the hardest time typing that, as well as n is in the integers. Right, and with that, voila, it satisfies both the left and the right. So let's copy this and do something similar for the top and the bottom here. So here's the bottom of the system, and here's the at any x and a y equals b. Yeah, there we go. There we go. True, 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 true. So yeah, this solution here definitely satisfies the boundary conditions. How about making sure that it satisfies the original PDE? So let's verify that UMN satisfies the 2D wave equation, right? And just to refresh our memory here, right, I think the wave equation, it might behoove us to write this down so we know that what we're trying to calculate in Mathematica. So I think we said the 2D wave equation was partial, you know what, this is going to take me too much time to sit here and fat finger, so I'm just going to copy paste it in from the notes here. So this was the governing PDE, right? It was the 2D wave equation. All right, so let's do, how about, you know what might be easier? Let's do the left-hand side. Let's calculate this first here. So the left-hand side of this is just the partial of u, x, y, t, right, with respect to t twice, right? So that's the left-hand side. It's this ugly thing here. Maybe let's just have Mathematica simplify that a little bit for us. Nah, that doesn't get too much better. You know what? Who really cares what it is? Let's suppress the output, because all I really want to make sure is that left-hand side equals the right-hand side. The right-hand side, I think, is, all right, that is c squared times the quantity. Basically, I need to take a bunch of these second derivatives here, but instead of taking it with respect to x, I'm going to take it with, or sorry, instead of taking it with respect to t, I'm going to take it with respect to x and with respect to y. So great, that ought to be the right-hand side. All right, so now here's the moment of truth here. Does the left-hand side equal the right-hand side? Yay, look at that. It totally worked out. So I think we're good. We have the eigenfunction. We have the eigenvalues. So now let's move on to our example here of the square plate, or the square membrane. Sorry, it's definitely not a plate, right? A plate would have some resistance to bending, which would violate one of the assumptions here. So this is really a membrane here that we're dealing with. So in the interest of simplicity, let's go ahead and just choose, how about A is equal to B is equal to 1 here? And heck, you know what? Let's also say C is equal to 1 here, right? So the thing is a perfect square of 1 meter, and the tension and the density work out in such a way that this C constant just comes out to be unity here. Okay, so maybe the first thing that we should do here is let's get a lambda mn value here. Actually, you know what we should do is let's pick specific values of m and n here. So let me just write that down here. Let's pick specific values of m and n. So maybe the easiest thing to do here is let's make an m. How about a m plot? Let's call a variable m plot, which is what value of m I want to plot, and let's make a variable called n plot, which is what value of n I'd like to plot. Let's just start with the 1-1 mode here, right? So with this here, let's go ahead and whoops, sorry, I should move this up to the other cell so we're all doing this all in one shebang. Okay, so now, what is the eigenvalue / frequency associated with this mode, right? So all I need to do here is take this lambda mn and say, all right, everywhere you see an m, replace that with m plot. Everywhere you see an n, replace that with n plot. And then I think anywhere you see a, replace it with a 1. Anywhere you see a b, replace it with a 1. Anywhere you see a c, replace it with a 1. All right. So hopefully that gets us a value. Here we go. Here it is. So the frequency is square root 2 times pi radians per second. It might actually be helpful to get that in like hertz. So maybe let's do a frequency in hertz. So that should just be, you know what we should do? Let's make this a variable, mn plot here. So this is the specific value that I'm looking at here. So if I take this and divide by 2 pi and get as a number, this should give me the frequency in hertz. So great, this first mode is a little less than a hertz. It's 0.707 cycles per second here. Okay, so now let's go ahead and plot this here, right? So let's go ahead and say plot / visualize UMN, right? So what do we got here? So I've got a UMN at X, Y, and T here. And again, let's make our substitutions of what are the M, N, A, B, C values that I'm looking for here. Here we are. And you know what we could also do here? Without a loss of generality, let's get rid of these coefficients BMN and BMN star. That might be easier to look at here if we just say BM is 1 and BMN star is 1. Okay, here we go. So we've got ourselves a function. Let's call this, how about UMN plot, just to keep going with this theme of calling something plot here. And now this is just a function of x, y, and t. Okay, so here we go. This is the function that I'd like to visualize. So let's go ahead and plot this here. How about at time equals 0? So I could go ahead and plot 3D UMN plot of x, y, and at time equals 0. And maybe let's make x run from, I don't know, how about 0 to 1? Actually, that's what we should be doing, right? Because we said this is a square plate here of, we assume that a is equal to b is equal to 1. So it's got 1 meter. So let's just make it go from 0 to 1 here. And we'll make y also go over the range of the plate here. There we go. And I think we should, here we go. So here is our thing at time equals 1, at time equals 0.1 seconds, a little bit later. And you know what might actually be helpful is, let's make it so Mathematica doesn't automatically change the plot ranges here, and doesn't automatically scale. So let's make the plot range go from x going from 0 to 1, y going from 0 to 1, and we'll make z go, or the deflection go from, how about -1 to +1. Something like this. Whoops, and actually looks like that's cutting this off a smidge. Yeah, whatever. This is probably okay. Because you know what? Actually, I don't want to just sit here and do this by hand here. Let's manipulate time here. Let's animate this so we can see what happens as time progresses. So I'll put t in here, and I'll wrap this entire thing with the manipulate command to say I want t to go from time 0 to, let's get, how about 1 oscillation of this, and this is why it's really nice that we actually computed the frequency of the oscillation. So if this is the frequency of oscillation in hertz, the period of the cycle should be 1 over that, right? Okay, so there we go. Let's try this. And now we're in business. This is looking pretty good. So if you look at this, well, I guess maybe let's make this plot a little bit bigger. How about 1.5 to 1.5 maybe, so that maybe we don't have this issue here. Here we go. All right, sorry, I'm back. The screen capture timed out here, so let's start again. So maybe let's see if we can zoom. Let's look at this kind of edge on here, and now here we go. What? Why is this? There we go. Great. So we see this thing moving up and down and up and down and up and down, right? So this here is basically the 1-1 or the base mode of this system here, right? Okay, let's take a look at this. How about, what if we wanted to change m and n? Let's look at, how about the the m equals 1, the n equals 2 mode. So all I need to do is shift enter this again. And then I think I should just be able to shift enter this. Yeah, I think, yeah, this should all work, and shift enter this again. Here we go. All right, so here is the 2-1 mode here, right? So we see we get this interesting condition here. Again, notice boundary conditions are totally satisfied. The edges are not being deflected. But this thing now has sort of these nodes that go in opposite directions. And again, notice here, here's our frequency, 1.11803 hertz. And make a note how this looks like, right? So you got these two nodes that are, the way we have it oriented, it's longer in this direction, and the doubles are sort of in this direction. So if I switch this here, let's look at how about the 2, 1, right? If I change this, shift enter, I get the exact same frequency, so the eigenvalue is the same, but this mode is now flipped. So if you look at this here, you still get these two, but now they're sort of 90 degrees from where they were earlier. So again, this is really interesting. You can get these situations here where you have the same eigenvalue for different eigen functions here, right? Yeah, so this is actually kind of fun. I don't know, for giggles, maybe let's do the 713. Let's see what this guy looks like just for fun here, right? So if I look at this, oh boy, look at this. It looks like a bunch of eggs running all over the place here, like an egg carton here. But here we go. This is this other interesting oscillation mode of this plate here. Okay, so I think we've got the eigenfunctions licked here. We know how the system operates sort of in these base modes here. How about now thinking about moving on and getting the solution to the entire problem to an arbitrary initial condition? So let's jump over to the whiteboard to get the total solution. All right, so we've got the eigenfunctions and the eigenvalues set up. So let's just go ahead and work on step 3, which is go ahead and compose a total complete solution that satisfies the initial conditions, right? So the way we're going to do this is like we've done earlier, is we are going to say that this total solution that we're looking for here, right? This is what we were going for. Let's just use a Fourier series. In fact, it's going to be a double Fourier series of taking all of these coefficients, or these eigenfunctions, u, m, n, right? And let's just sum these from n equals 1 to infinity, and also sum from m equals 1 to infinity here, right? Because I've got two indices, m and n here. Right? Okay, so let's just write this out one more line here, maybe. So I got my double sum from n equals 1 to infinity, from m equals 1 to infinity. Okay, our eigenfunction was our big expression we had earlier, right? This was b m n cosine of lambda m n t plus b m n star sine of lambda m n t. This whole thing times sine of m pi over a x times sine of n pi over by. Right? Okay. So what we'd like to do here is at time equals 0, right? This should equal our initial displacement, which I think we said was our function f of xy, right? That was our notation here for our initial displacement. So let's go ahead and plug in. I need u of x, y, and at time 0 to equal this function f of x, y. Okay, so at time 0, I basically take this whole thing, right, and I jam in time equals 0 everywhere. So if I do that, this thing looks like, you can write this as a, whoops, sorry, missed my double summation here, right? Let's put the double summation first. Summation n equals 1 to infinity and m equals 1 to infinity here. We end up with just a b m n sine of m pi over ax times sine of n pi over by, right? This whole thing better equal f of xy, right? So, all right. What we can do here is recognize that, again, if you think about what we're doing here, we're saying I've got a two-dimensional function here, and I want to compose this two-dimensional function out of a whole bunch of sine and cosines here. So again, Fourier series should be shooting off in your head here. This is what's referred to as actually a double Fourier series of f and xy here. So the way we're going to do this here is, first, let's go ahead and set or define, maybe let's just look at the components that have to do with y. So if you look at this here, it's this sine of n pi over by here, right? And maybe this constant. Let's define another function here here. So let's go ahead and say, first here, let's set this function. Let's call the, we'll grab the summation from n equals 1 to infinity here of bmn sine of n pi over by, right? This is all of the y terms in the above expression. This is just a function of y. If you look at this, right? This is constant, bunch of constants, and here's the only y in here. So this whole thing is just a function of y here. And furthermore, it's also a function of m here, right? Because we're going to sum out the n values, and are going to go from 1 to infinity. So the only things that's going to be left in here are a changing m and a changing y. So we could denote this as maybe, I don't know, let's call this, how about a km of y, right? I'm just rewriting it instead of having all this stuff. I'm just going to write it like such. If so, I can rewrite this, this infinite series, this double infinite series, like this. Let's write it over here to get ourselves a little bit more space. So we have the whole thing. This is going to equal f of x, y, right? Is that what I'm looking for? This thing now looks like summation from m equals 1 to infinity here of km of y sine of m pi over ax, right? Okay, so now for a fixed y, if you look at this, let's assume y is fixed here. What this looks like is you have on the left side, this is some function of x is equal to, these are a bunch of coefficients or constants, right? And then you got this sine expression as a function of x. So again, you're trying to now, for a fixed y, look at how do I make a function, an arbitrary function of x, using a whole bunch of sine x terms here, right? So if you look at this long enough, this is basically your single normal Fourier sine series of f of x, y here, right? So if that's the case, the coefficients or the constants of these sines here are given by your normal Fourier expression that we explored in most of these other previous lessons here. So in this case, we can basically say that, you know, km of y acts like the coefficients of a Fourier sine series of f of x, y, right? So in other words, those coefficients, right, let's say km of y, right, this was given by a very specific formula that we already derived and used earlier. So in order to get these coefficients, right, you go ahead and you take the function you're trying to recreate, right, which is f of x, y, right? You multiply that thing by sine of m pi over x, right? You integrate from 0 to a over the period, and you go dx, and then you normalize this thing by 2 over a, right? Okay, great. Great. All right, so here's first, so let's I don't know if I want to box this up initially. Maybe sure, let's box this for now. We're going to come back to it in a second here, right? And now let's come back and look at this. Now, if you think about this, sorry, do I have, anyway, hold on, did I put the wrong thing up there? Sorry, hold on, crud. Yeah, sorry, this should have been a y, right? Wait a second. Let me make sure I didn't, km is bmn, n pi over y, right? And then we plug that in. Oh, yeah, right, because this, no, this was correct. This was correct. This was correct. Yep, okay. Okay, perfect. All right, so we're still okay. What we should now do here is, let's come back and examine how we define km of y. If you look at this, we said that, all right, the left side is some function of y. And again, you're trying to make this function of y by just summing a whole bunch of sine waves here. And here are the coefficients of the sine waves. So again, if you look at this expression here, this is just another Fourier series. And the coefficients of the Fourier series are right here. And we should know how to calculate that by using a very similar expression of what we just did here, right? So in other words, let's write this down. So let's go ahead and say that, you know, we consider bmn, right, acts like the coefficients of a Fourier sine series of f of x, y, right? With now the understanding that x is constant, but y is not here. So in other words, the coefficients that we're looking for are b, m, n, right? This was given by the, a very similar thing, right? The way you compute those here is you go ahead and you take the function that you're looking for. So in the function that we're trying to recreate again is that kmy. So I got km as a function of y here, right? I multiply this by sine of n pi over by, and I integrate from 0 to, that should be a 0 to b, right, dy. And then I tack on up here a 2 over b. Right? Great. So now, if you look at this, what we were gunning for here is actually, I want these BMN coefficients. I can now take my expression for KMY, plug it into here, right? So maybe let me grab another color, right? Take this entire thing, right? Substitute in right there, right? Let's do that here, and we're basically home free. Maybe let's keep this expression up because I don't want to have to rewrite that whole thing here. Okay, so what we end up with here is these coefficients b, m, n, right, is going to be, well, once you substitute this, and you'll see there's a bunch of stuff that can cancel out, or sorry, be pulled out of the integrals here. So in the interest of saving time, let me just do all the simplifications here of, it's really just algebra, right? Just jam that integral into here and pull some stuff out. So you can write this whole thing to look like 4 over ab, integral from 0 to b, and the integral from 0 to a of f of xy, sine of m pi over a x times sine of n pi over by dx dy, right? Here with, again, m and n are integer values here. So here we go. This is really what we want to box up, because this is how you're going to calculate the coefficients of this here, right? This is our double Fourier series here, effectively. And if you do this, we should be able to satisfy the initial displacement, right? So all you do is you take this initial displacement. I don't know what it looks like. It could be anything, some crazy function here. And if you just run through this double integral for each value of m and n that you're interested in, you should be able to get the coefficients for your total solution that will satisfy the initial displacement. So the initial velocity is actually a very, very similar issue here, right? So we could follow almost the exact same routine here, or the exact same logic. So just to make sure we're all on the same page here, what we need to do now here is we're going to say that, all right, let me take a derivative of this, because I now need to, the position meets a specific requirement, but I need the velocity at time 0 to meet a specific requirement. Namely, I need partial u with respect to t at x, y at time 0, right? So here is my initial velocity of the membrane here. This has to equal some g of x, y, some other specified given distribution here, right? Well, you can go ahead and take the derivative of this thing. You see that with respect to time, you see what's going to happen here is a lot of these lambda n's are going to pop out here. And I guess you're going to change this. So we'll tell you what. Yeah, let's just do it here, so we're not skipping steps here. So n equals 1 to infinity, m equals 1 to infinity. So I think if you take the derivative of this entire thing, what we got yeah, lambda mn is going to pop out of the outside, and then we end up with a bmn. This should now be a minus sine lambda mn t, right? Plus bmn star sine of lambda mn t, right? This whole thing times this bit here, right? Times sine of m pi over ax times sine of n pi over by. Right? Now I need to take a look at this at time equals 0, so this term is all gone. This, oh shoot, nope, sorry, this should have been a cosine, right? Because you take the derivative of sine, you should get cosine here. So this whole thing should now go to just 1. So this is great. So actually the only thing now, so here's where we see the BMN stars come into play, but it's actually BMN star times lambda MN here, right? So let me write it down real quick here. So the last thing we end up with here is this thing looks like BMN star times lambda MN sine of M pi over AX times sine of N pi over BY, right? This whole thing is got to equal G of XY. Okay, so if you look at this thing, this is identical to what we just did earlier, except instead of finding a coefficient BMN, it's now finding the BMN star times lambda MN. So it's basically, you get, shoot, I erased it. F. Well, you would get the same results here, so I'll tell you what, let's do it over here. Let me rewrite what we ended up with earlier when we were doing the initial position. So I think initial position, I think we said was BMN is equal to, where was it? Yeah, 4 over AB integral 0 to B, 0 to A of f of x, y, sine of m pi over ax, sine of n pi over b y, dx dy. Let me just make sure I got that right. 4 over ab 0 to a sine m pi over ax. Yeah, sine m pi. Yeah, okay, right? This is what we got earlier. So now all we're doing now here is this is the exact same thing, except now on the left side, this is BMN star times lambda MN, right? And this is now a G, right? So really the only thing I need to do is just move this lambda MN over to the other side, right? So this is lambda MN, right? And that's basically it. So here we go. Here's how we're going to get our coefficients BMN star. So we're done at this point here, right? Here is our total solution right here, right? This was u of x, y, and t. This is what we were looking for, right? So now we know that this thing satisfies the boundary conditions, and due to superposition here, we know that this thing satisfies the 2D wave equation. And now we know how to calculate the BMN and the BMN stars such that this entire thing also satisfies the initial conditions in position as well as velocity here. So, I'm actually not going to run over to Mathematica and plot this and do this here because I think this is enough of a formulaic cookbook that you can now just go ahead and turn the crank to do it. Plus, we have a homework assignment on this, so I don't want to give away all of the secrets here. So I think it would behoove you to get a little bit of practice actually doing this for a practical problem. So, with that being said, I think this is a good spot to stop where our discussion of the 2D wave equation here in Cartesian coordinates, right? If you think about this long enough, everything we did was in Cartesian coordinates, right? Everything is dx, dy here. So what I want to do next here is actually discuss cylindrical coordinates here, right? And some interesting behavior that comes out of this if we wanted to look at this for, say, like a circular membrane instead of a rectangular membrane. So, I hope you enjoyed the video. If so, please subscribe to the channel. We're going to have a lot more videos related to math as well as other engineering and software tools here. And it really helps me out if you could subscribe here. So, with that being said, I really hope to catch you at one of the future videos. Bye.